All right. Good afternoon, good morning, whatever time you are watching or viewing this training material. Today we are going to be going forward. Our previous lesson we discussed conduit, conductor, installation, and conductor. We talk about the wiring, conductor, and wiring. Now we're going to talk about sizing wiring, how to size wiring sizing for your system, sizing wiring for your PV system. I'm going to dive right into the training, sizing wiring for your PV system. So I move right over here. I'm going to first right to this material. I'm going to go right ahead and talk about um, sizing conductors for PV system. Um, so we're talking about sizing conductor for PV system. And I'm going to give you the overview of the learning objectives of today's training. Today objectives of today's trainings. I will identify terminologies for the various sockets in PV systems. We will determine the maximum current for PV system sockets. We will define continuous detail as applied to PV system sockets. We identify and describe considerations for selecting conductors to meet amplicity and voltage drop requirements. We also choose wire size for PV source socket and inverter output socket. So that is what we're going to be discussing today. That is our main material, our training material today on sizing conductor for PV system. As mentioned previously, it is critical to understand and use correct terminology when discussing PV sockets. This lesson will cover the different parts of sockets and PV systems, define continuous detail, look at how it applies to PV sockets. We will also discuss how to determine maximum current for PV system socket. We identify and describe considerations for selecting conductors that meets both amplicity and voltage drop requirements. Choose a wire size for PV source socket, inverter output socket, and inverter output socket. Complete conductor sizing for photovoltaic systems is a complex and lengthy process. This presentation is not a step-by-step sizing guide, but an overview of the relevant considerations and definitions. Conductors will be selected using tables calculated using conservative worst-case scenarios. Design values. These tables present conductor choice that meets the NEC requirement, but may be overly conservative, oversized in some situations. Online calculator will be used to verify that proper voltage drop parameters are met. So buckle up, sit up right, open your horizons of your mind. We're about to dive in a very important aspect when it comes to building a PV system. Sizing conductor is very important. After completing this lesson, students should be able to identify terminologies for the various sockets in PV systems, determine maximum current for PV system sockets, define continuous detail as applied to PV system socket, identify and describe considerations for selecting conductors to meet amplicity and voltage drop requirements, choose wire size for PV source socket, and inverter output socket. So that's what you should do. Upon the conclusion of this training, you should be able to understand these various topics. All right. Now we have a diagram here, sizing conductor for PV system. When you look at this conductor here, we have PV array. 1, 2, 3, 4, 1, 2, 5, 6. 1, 2, 3, 4. So this is 24 panel. This is 24 panel. It's a 24 panel array. Arrayed a group of panel of PV models together. We call them array. And now you notice that they are in series. Series number 1, series number 2, series number 3, and series number 4, because 24 divided by 6, 24 divided by 6 equals 4 times. So you have 4 segments of 4 series of this PV array. Now, 4 PV source sockets. If you look here, we have the DC combiner, we have the DC combiner box. We have the DC combiner box. The DC combiner box, all of these sockets here, if you look at the positive, are running toward the DC combiner box, and the negative are also running to the DC combiner box. Now, 4 PV source sockets. If you look here, these are connected in series. We have one, we have connecting positive, negative, running to the combiner box. So the combiner box, all of when you pair your models in series or parallel, you're going to run one cable toward your combiner box to represent each segment of your series. So there's one negative going in there and one positive going into the combiner box. We explain it further. Notice that from the combiner box to the DC disconnect, we have two conductor moving forward. We have one positive and one negative. One negative and one positive moving forward from the combiner box to the disconnect. Why is the disconnect important? We discussed that earlier in one of our chapters. Disconnect is very important. You have to have it. There's a PV socket. If you notice here, this disconnect, in case there is any reason for maintaining or doing any work on the model, on these models here, the technician can come to the disconnect and disconnect this PV array, this DC components from the rest of the house appliances or connections. So the disconnect is very important. In case of any trouble, you can just run to the disconnect and shut it off. That automatically disconnect these components of your configurations on the system from the AC if you have an AC and DC connection if you have them. Now you notice that we have this disconnect here. We have two cables running from here from the combiner box to the DC disconnect. Now we also have PV opposite showing the opposite here. Another PV opposite here. From the disconnect to the inverter, we have another cable going there to the inverter. From your inverter to your AC service panel, there is an AC disconnect. There's an AC disconnect. Why does we need an AC disconnect? We need an AC disconnect for any reason whatsoever. We want to work with the AC component section of our system. We can disconnect the AC from the rest of the connections from the inverter, so the inverter cannot convert or change the DC into AC, and so that the technician can safely work with the AC system. Inverter output socket, right? Now let's move forward. The National Electrical Code (NEC) defines PV source sockets as sockets between models, and from models to the common connections of the DC system. NEC 690.2. That's a very, if you are a technician in the United States world, you have to get acquainted or abreast with the Bureau Code, NEC code Many installers use the term series string, which is another name for PV source socket. This schematic, the common connection point is the combiner box, meaning each of the socket between the modules and the DC combiner box are PV source socket. Each of the connection between the modules and the DC combiner box are PV source sockets. There are 4 series string PV source sockets of 6 modules, and the positive and negative wire from both ends of each of the string are considered a PV source socket. The wire connections between each module are also considered part of the PV source socket. These are module LED leads that are part of the module assembly, and the only action required for those sockets is making the connection. Those module leads and connectors should never be modified. The module leads and connectors should not be modified. So in the various sockets right here, 4 PV source sockets in this whole connector. We have socket 1, socket 2, socket 3, socket 4. Group, this is one socket. There's another socket. This is one socket. The inverter output socket. This is another socket. So we have 1, 2, 3. We have 4 sockets. But it is just used for what? Right here. See, very key point to understand what the sockets. We have 4 series string PV source sockets, 6 modules, and the positive and negative wires from both ends of each string are considered the PV source socket. The wire connections between each module are also considered part of PV source socket. These are module leads that are part of the module assembly, and the only action required for those sockets is making the connections. Those module leads and connection should never be modified. They should never be modified. They should never be modified. Do not try to modify. Not to be modified. Okay? Let's continue. The NEC 690.2 defines PV output socket conductor between the PV source sockets and the inverter or DC equalization. In the schematics, the PV output socket is formed by the conductor between the combiner box and the DC connect, as well as between the DC disconnect and the inverter. The PV output socket is created by combining multiple PV source sockets in parallel. In systems where multiple source sockets exist, the PV output socket increases as the number of the parallel PV source sockets increases. Some PV arrays only have a single source socket, so the source and output sockets are the same. Same thing. In such cases, large PV systems have multiple combiner boxes, few by numerous PV source sockets, thus have multiple PV output sockets. But then here, our PV modules here are connected in series. Positive from this module to the negative of the second module. Positive from this module to the negative. So these are all series connections. Then we have a parallel cable, which is a negative parallel moving from this series of 6 modules, moving straight toward your combiner. We also have a positive moving straight toward the combiner. You notice that the negative and positive are separate. All negative sockets are on the negative are connected here separately. Positive are also connected here separately, so they are not combined. Or it should never be combined. Should never meet. Causing disaster. Combine negative and positive, and then electrical connection. I've seen that appropriate, not in current, don't do it. So that's what you notice. So we have our sockets all runs, all the runs here. We have different sockets combining here, combining. Now these sockets are not used. These combiners here are not the one that is supplying to the various outlet in your house. They are just used for connection between your various devices. When your inverter, your AC disconnect, your AC disconnect, your DC disconnect, and your AC panel box to the grill. Now this connection right in this graph right here, you use the grill. So this is a grill task. This is a grid direct system, which means they also have input of AC input from the grill, which means LEC current we're saying like this. So this is a grill direct assembly, a grill direct drive. It's not a battery-based system. This is a grill direct design right here, just to let you know, which can also be used for if you have a generator where you can have a second input of AC input of current coming into the home as well. If you have a generator, this is a beautiful setup. That's why you don't see a charge controller, you only see an inverter. Now let's move forward. PV output circuit is created by combining multiple PV sockets in parallel in a system where multiple source sockets. PV output current increases as the number of parallel PV source sockets. Some PV arrays only have a single source, so the source and output sockets are the same thing. In such cases, large PV systems have multiple combiner boxes filled by numerous PV source sockets and thus have multiple PV output sockets. The inverter output socket is defined as conductors connected to the AC output of an inverter. In the schematics, the inverter output socket is formed by the conductor between the inverter, the AC disconnect, and the main AC service panel. Sizing the conductor for PV system. We have 20 PV source socket right here. Now, in this connection here, in this drive, we have a macro inverter. So this is a whole different skin of things. Macro inverter. What does that mean? It means that from up on the roof, current, the input of current or power that comes into the home are inverted from from DC AC from the panel directly. What the inverter does, it changes the DC current to AC current on the top of the roof. So you notice that one of the beautiful thing about the microinverter, if there were any scenarios wherein if we have um shade, shade on top of a shade or a soiling, maybe the dust or wind blow a lot of dust on the model. If you have an inverter, a microinverter, what would be the only thing that would be affected, only model that would be affected is the model that has shallow or sorting. Unlike this connection where you have a series connections of 6 model each, if one of these models are affected, it affects the entire group. One of these models are affected. One of these models here has a shading or sort on it. It will affect the entire series. That's one of the disadvantage of this connection versus using a PV in a microinverter. Microinverter they are used a lot in developed countries, and they are used more like in commercial settings a lot. So if you notice here, we have our each inverter has its own microinverter. Each model has its own microinverter. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The total of 20 PV modules, and they are all connected in parallel. So, negative, positive, connected to this socket, parallel, socket, parallel, this socket, parallel. You notice that negative and negative is a negative from one series, one string, or one socket to your junction box, Now, then we have the positive. Take the positive from each of those connections, moving over to your AC combiner box. If you're a technician who have done a lot of AC connections, you will be familiar with some of these connectivities. So right here we have two inverter output socket, one inverter socket. We have two inverter output socket. We have a negative and a positive inverter output socket. Now, if you notice that there is not an inverter in the house, because from the model, the DC have been inverted to AC using the microinverter. So directly coming into this home are all AC current, are all AC directly coming into the home, complete AC runs. So the lead sending all of these runs into the home, all AC runs. Explain it forward as the diagram shows an example of a microinverter system. By definition, source sockets are sockets between modules and from modules to the common connection points of the DC system. So the PV source sockets in the microinverter systems are the module leads, which connects to the microinverter. These module leads are the only DC wire in a microinverter system. Looking at the definition of the PV output socket conductor between the PV source sockets and the inverter, or DC utilization equipment. The module lead also fit these descriptions since they are located between the source module and the inverter equipment. However, they are commonly just referred to as source sockets since they are not combined. If you look over here, they are commonly referred to as source sockets since they are not combined. Beautiful. AC disconnect, AC combined panel, the junction box. Socket here, socket here. So this whole schematics, we have two sockets. Socket number one, bringing in the runs of the lead from the modules into the junction box. Socket number two, from the junction box into the AC combiner box. And we have from the AC combiner box to the AC disconnects. From the AC disconnects, the same runs move forward to your AC panel box. The inverter output socket is defined as a conductor connection to the AC output of an inverter. In this diagram, there are two inverter output sockets, one from each branch socket of 10 modules running through the junction box to an AC combiner panel. The output of the first two inverter output sockets are combined together in the AC combiner panel, and the resulting output socket is also called an inverter output socket. In fact, the entire socket between the AC combiner panel to the point AC combiner panel to the point of the interconnections will be called an inverter output socket, regardless of what kind of equipment may be included, such as meters or disconnect. It may also consist of several different wire sizes. We have another schematics. We have another graph right here. Two DC to DC converter output socket. Two DC to DC converter output socket. 16 PV source socket. 16 PV source socket. So we have 16 PV source socket. They are in series of 8. 1, 2, 3, 4, 5, 6, 7. This is series number 1. This is series number 2. Now, you notice that this is a different one. This here, we are not using a microinverter. We are using an actual solar edge inverter. Actual inverter. So we have all of our models in series number 1, negative, positive, negative, positive. They are all in series connected. We have the sockets running over here to our junction box. We have this here second DC to DC converter running all the way to our junction box. Inverter output, we have your inverter right here. This is a solar edge inverter. And the solar edge inverter, your runs go into your DC disconnect and to your grill, AC panel. This is a direct grill system. So it also have source of electricity coming from the grill, which is called LEC. That's what you notice here. Now, in these scenarios, your inverter is also the current that moves to your AC panel to your breaker. When in the day, when you are getting enough power from the sun, your meter will read backward. So you will be selling grill, you'll be selling current to the grill. And then in the evening, when the sun goes down, the meter read forward. So then current, your accessories, your appliances will now be powered from the grill. That's how it works. This is how it works. Or grill. There's no battery in here. There's no charge controller. There's no um, um, uh, inverter charger. No, this is strictly to the grill. Now the diagram shows an example of a DC to DC converter system. DC to DC converter source socket and DC to DC converter output socket are separately and individually defined in the NEC. DC to DC converter source socket are defined as socket between DC to DC converter and from the DC to DC converter to the common connection point of the DC system. In this system example, the two sockets from each string or series connected converters fit this definition since they are from DC to DC to DC to the common DC connection point. Common DC connection point. Right? However, they also fit the definition as well. DC to DC converter output sockets are defined as socket conductor between the DC to DC converter source and the inverter or DC utilization equipment. In this case, we will call the two sockets from each series string DC to DC converter output sockets, since each is carrying the combined output of all the converter for that string. The model lead in this case are considered PV source sockets, even though they are part of the DC to DC converter system. The inverter output socket is shown here between the inverter and the point of the interconnections in the AC series panel. Sizing conductor for PV system. Conductor size consideration. Conductor amplicity requirement, NEC requirement, show shift, voltage drop, requirement for good system design to ensure maximum system productions and proper operations. Too much voltage drop can lead to reduced production, system not operating. There are two primary considerations when determining an appropriate conductor size. One, amplicity. Two, voltage drop. These will be discussed in more details in the following slides. Correctly sizing conductors per the NEC means ensuring they have enough amplicity for the current in the circuit they serve, based on the physical and environmental conditions in which they are installed. This is a safety concern, basically to ensure the conductors are not overloaded, which can result in fire. Sizing conductor to minimize voltage drop to within acceptable limits is a good design practice, not a safety concern and therefore not a NEC requirement. The goal is to ensure that production is not lost and that the system operates correctly across all ranges of operational connections it is exposed. Beautiful. So if you look right here, let's go back to the conductor size and considerations. Conductor amplicity must be considered. We must also consider the NEC requirements, which is to ensure safety. And then we talk about voltage drop, requirement for good system design to ensure maximum system productions and proper operation. It is important to consider the fact that you want to minimize voltage drop. You want to minimize the voltage drop of your system. So sizing your conductor appropriately is very important. Sizing conductor for PV system, PV source and output sockets, sizing consideration. The National Electrical Code, ISC. The maximum socket current, the continuous operations 3 hours plus, the temperature and multiple conductors adjustments, device terminal and compatibility. Voltage drop IMP, the maximum power current, the minimum power voltage, the current length, the conductor resistance per foot. These are all important to take into consideration when sizing your socket. Maximum current, the maximum cost socket current, the continuous operations, 3 hours plus, the temperature and multiple conductor adjustment. They're very important. And your maximum power current, the maximum power voltage, the socket length, your conductor resistance per foot are very important. The National Electrical Code NEC address conductors amplicity, which for PV systems, DC sockets is based on the mileage shock socket ISC. Worst case amount of current that could be expected. Values for maximum and continuous socket current are calculated based on the definition in the NEC. The temperature and multiple conductors adjustment are applied, and device terminal compatibility is verified. A good conductor with the appropriate amplicity can then be chosen. With the appropriate amplicity can then be chosen. Let's look at voltage drop. Voltage drop is calculated to determine if the conductor size that meets the NEC amplicity requirement is also large enough to meet acceptable voltage drop design parameters. Drop in voltage equals loss of power, and some voltage drops is inevitable. 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 The key is limiting it to acceptable level. Voltage drop is an issue when the system is operational. The calculations are based on the maximum power current PV sockets as well as the length of the socket operating voltage (EMP), the resistant ohms per length of the selected conductor. Very important aspect to take into consideration. Very important. Right? So it is important to make sure that you try to minimize the loss of current, and may also cause fluctuation or the system shutting off. If you have too much trips, current keep dropping, you could shut off the system. Very important. Taking into consideration. If you use the wrong wiring, be a very big factor when it comes to having the right voltage. Take that as keynote. Now, DC to DC converter source and output socket sizing consideration. National Electrical Code continuous output current rating. The rated converter maximum output current, continuous operations plus 3 hours plus the temperature and the multiple conductor adjustment, device terminal compatibility, the voltage drop, ratings converter continuous output socket output current, operating voltage, the current length, the conductor resistance per foot, and the manufacturer limits. These are all important when sizing consideration. These are all to be taken into consideration when sizing output socket, output socket size. When determining conductor size to meet NEC requirement for DC to DC converter systems, the same principles apply that are used to calculate other PV source and output socket. However, in this case, the rates maximum continuous output currents of the converter used instead of the model IF. Voltage drop for DC to DC converter circuit is calculated using the same principle as PV source and output circuit. Since current is variable in these systems and can fluctuate frequently. Use the rate converter maximum output current rating for voltage drop calculations. In addition to the operating voltage, circuit length and conductor resistance length. Manufacturer of the DC to DC converters may have specified limit for voltage drop to ensure their equipment operate properly. Be sure to follow all manufacturer recommendations and required limit regarding system voltage drop. Be sure every wiring, every conductor, every socket have manufacturer requirements. They tell you how much of a run, how long, what distance, what temperature. It has read about whatever wiring or whatever sockets you are purchasing so you can know what the manufacturer recommendations are. Very important. One of the problems we have is that we don't like to read manuals. We want to build a big, but we don't read the manual. Now, inverter output socket size consideration. The National Electrical Code continuous output socket ratings. Rate inverter maximum output socket. Continuous output. You notice that the continuous operation is 3 hours plus. You also notice that the temperature and multiple conductor adjustment device terminal compatibility. For voltage drop, we have rate inverter continuous output current, normal AC voltage, current length, conductor resistance per foot, the manufacturer limit. There are some similarities as we go along. Inverter output socket size in consideration, and we'll go back here to the PV source and output source socket size in consideration. Conductor resistance per foot is also there. Conductor resistance per foot. So there are some similarities when choosing the right conductors for the various connections. So between the inverter, that what it's saying, size in consideration, output socket size in consideration for inverter. Let's go back there. So this is your inverter right here. Let's go back to this uh, right here. This runs here from your junction box to your inverter and from your inverter to your AC disconnect. That's what they're talking about. The sockets runs right here. They're telling you what are the requirements for the sockets you're going to use between your junction box to your inverter and from your inverter to your AC disconnect. So they're telling you what the requirements are, what what different, what things that need to be considered, what wiring you should choose, what conductor use a well conductor or socket. For your inverter, the national code is there. It should be rated inverter maximum output socket. Con- Rate inverter maximum output socket. The continual operation should be 3 hours. The temperature and multiple conductor contract adjustment. The device terminal compatibility. Rate inverter continuous output current. The normal the normal AC voltage, the socket length, the conductor resistance, the fault. The manufacturer have to reorder that. Have all those information. You choose the right. So 85% of the time when it comes to system size and system configuration, if you use the right, it's like when you're cooking and making a soup. If you use the right ingredients, the right seasoning, the food tastes good. And people will praise the food you have cooked. It's the same way. If you use the appropriate wiring, follow the right guidelines. And don't say you just do things because it's Africa. Let's do it the African way. Let's just do it the African way. Standardization is very important. Because if you get used to doing things the African way or the Liberian way, wherever, tomorrow when opportunity arises that you have to be put in the situation in the place where you're supposed to use the right, follow the right background or the right way things should be done. Now you are so comfortable doing bending the curve, you can't do the right thing. So try to familiarize yourself with the right precedents, the right requirements when it comes to sizing or installation of PV model. It is very factor. Now let's look at the PV source socket output socket minimum, the maximum current. If you look in this diagram here, this graph, we have a house here. We've seen a house, a building with the model, PV model on the top of the roof. How beautiful, what a beautiful installation. See right there, mounting over, mounting on that. PV source, and PV output socket. The maximum current. Environmental conditions can excel STC ratings 1000 WMA. So take that into consideration. Clear day with snow reflections, high altitude locations, high latitude location, maximum PV socket current equal the AISC times 1.2 radiance factors. The maximum current and amount you could actually measure with clip on clip on meter. Measure that with a clip on meter. NEC section 609.8 define the maximum current socket current or maximum current for PV source and output sockets as a sum of parallel connections PV model rates short socket current times 1.25 number of socket in parallel times ISC times 1.20. This 1.25 factors is applied to the rating short circuit current because certain conditions such as clear day with snow reflections or high latitude location can result in PV model operating above the STC rating for several hours. The saying here, places like America or environment where they have snow, and also there are conditions with high latitude and sometimes they may go above the SCC ratings for several hours. Basically, maximum circuit current is an amount of current that you could actually measure if there was a short circuit and the sunlight intensity was above 1000 WM, a current test with a clip on clip on ammeter could result in reading of this maximum level of current. There is a meter you can use, the ammeter, that you can clip on the wiring on the socket wires to tell you exactly what the maximum current you are getting through that wire. In a system with two PV model sockets, the maximum socket current of each PV source socket will be modeled ISE times 1.25. The maximum socket current PV output socket consisting of those two PV source sockets connecting in parallel will be sum of both source sockets. A little bit. For example, a 500 watts inverter. This given current value may vary slightly from what it would be if you manually calculated it using the inverter rated wattage divided by the AC operating voltage. For example, a 5000 watts inverter operating at 240 volts will have a maximum output current two near two near 20.83 amps. 5000 watts divided by 240 volts equals 20.83 amps. However, always use the manufacturer provided value, not this calculated estimate, as the inverter may be specifically programmed to produce the exact voltage given. Now let's go over this. NEC section 98.8 define the maximum current inverter output socket as the inverter continuous output current. Inverters manually inverter manuals and most specification sheet list an inverter maximum continuous output socket. So these informations are given. You buy an inverter, the inverter has a manual, it has a data sheet, and these information are given. One problem is that we just chunk the paper away and just start doing the job without reading these manuals that tell you exactly what you need to do. So you install a program, you start doing your installation, you start having trips, you start having the system shutting down because you fail to hold that manual and read about the maximum current for that inverter output socket. Very important. Inverter manuals and most specific specification sheet will list an inverter maximum continuous output current. This given current value may vary slightly from what it would be if you manually calculated it using the inverter rated wattage divided by the AC operating voltage. For example, if you have a 5000 watts inverter, if you have a 5000 watts inverter operating at 240 volt, you have a maximum output current near 20.05, 20.83 amps. 5000 watts divided by 240 volt equals 20.83 amps. Very important. So for quick calculation, if you have a 5000 watts and the volt, which is so on my pen, man. Mm, mm. Okay, use it. Okay. Um, I'm gonna use my apply already. Technology. Hold on one second. For this thing. Right. Okay. So we have a 1000 watts inverter and the volt is 120. Now, if you look back to our material. So for example, a 5000 watts inverter operating at 240 will have a maximum output current near 220.8. Now, it's simple. The watts divided by the volt. So if we come right here to my example right here, we have the watts divided by the volt. Bring my calculator to show you. All of these information are typically available on the on the calculator. 1000 watts divided by 120. So 8.3. Sorry, system. Play my system. 8.3. Come on, man. Okay, we're back. Oh, great. All right. Sorry for that interjections. So if you notice right here, if I go back to my material, example here, for example, now you using your own, you want to use your own calculation. Simply, you on the field, you have an inverter. You don't know what is the maximum current for that inverter. Maximum current, the inverter output socket. You don't know the maximum uh, inverter current output socket. Maximum current for the inverter output socket. You don't know that. But you have the inverter in front of you. The NEC code 90.8 gives you a simple calculation, a simple way to determine what is the um, maximum current for that inverter. It says you look at the watts of the inverter, you divide it by the voltage. That's what I did right here, just to do a small number. I said right here, we have an example inverter size of 1000 watts. The volt is 120 volt. So we have 1000 watts divided by 124, we have 8.3. So your maximum, so your 8.3 amps, that would be 8.3 amp. That would be your maximum current for that inverter. The maximum current for that inverter. Maximum output socket for that inverter would be 8.3. Anything above 8.3 will cause a problem. That's what they're saying here. I want to go back up here. Let's start from here. Let's start from the NEC code 9.9.8. I like to go over things that we will understand it together. Go back. PV source and PV output socket maximum current. The environmental condition can exceed STC ratings 1000. Clear 1000 W square meter. Clear day millimeter. Clear day with snow reflections. High latitude locations, Liberia, Ghana, Sierra Leone, West Africa, we have a high latitude. The maximum PV socket current, the ISC 1.2, that is the irradiant factors. You must say that. So look here, the maximum current, maximum socket current, maximum current for a PV source output socket as a sum of parallel connected PV model rating short current is times 1.2 number of socket in parallel uh, times the RSE times 1.5, 1.25. So if we look at our series here, the socket between here, that's what we're talking about. The sockets between the models here, the sockets here. These sockets, what we're talking about there, we're talking about these sockets here. What is the maximum current, maximum output current? That's what they're talking about. You have to know all of this information. You have to get them. This is life. Playing with people's lives when you install any electricity and any source of electricity it has to do with life. So you take your time, learn the right thing, and do it right. So let's go back there and talk about the ratings. Ratings are already there. Well, most of these information I found in the manual. The data sheet, it gave you all of this information, but just practically, just trying to just say practically you don't have access to the manual, what you can do. So that's what they're talking about here. PV source and output socket as a sum of a parallel connection PV model rates short socket current times of 1.25. So you have to know the PV model rating short socket. You have to know that every PV model has have a PV model rating short socket. I want to check that out. I want to look on the nameplate of the PV model. Hold on 1 second. I'll come right back. So I can find out. I have. Data sheet. Where I'm back. All right. So I just share. This is a QPIC. It's a dual LLGS. This is a data sheet from the manufacturer for a PV model. The new high performance model is called the QPIC Dual LG5, LG 5.2. So this is the data sheet of a PV model. PV models come with a data sheet and the installation manual. It's available. You can go on the manufacturer website, you can download it, or it comes with the models. I usually download up to the most recent ones. So if you notice here, we have the mechanical specification. The data sheet tells you the mechanical specification of that model, what we call solar panel. It tells you. So it tells you that the format is a 2015 times millimeter times 1000 millimeter. They're talking about the format of the model, the weight, the front cover, the back cover, everything from everything is specified. But that's not what we want to talk about. We want to talk about electrical charge characteristics. Now, when you notice here, we're talking about socket. They say right here, the power short socket, the short socket current. The amperes, the amp is 10.503. That's the amp. ISC 10.05. The open socket voltage 47.95. That's for a 380 watts. For a 385 watts, 10.10, 84.2. 390 watts, the ones I always have, 10.14, 48.48. 395 watts, we have the short socket, 10.19, 49.74. So these information, that's the minimum. Then we have your maximum. That's now we're discussing the maximum. The maximum performance at normal operating conditions. Go back to my note right here. Maximum current, maximum socket current. That's what we're talking about. ISC. Here is the ISC rating for this panel. ISC ratings right here. For 83 volt, we have 8.11. For 385, we have 8.4. So the information you need is always available on the data sheet. The data sheet tells you what is the maximum socket ratings of that PV model. Now, so that's so that's why this is what we're talking about here. We're talking about the maximum current socket for PV source and output socket as a sun parallel connection. PV model rating shook socket current times 1.25. number of socket in parallel times the ISC rating 1.25. This 1.25 factor is applied to the rating short circuit current based on certain conditions, such as a clear day with snow reflections or higher latitude locations, and result in the PV module operating above the STC rating for several hours. Basically, maximum socket current is an amount of current that you could actually measure if there was a short circuit and the sunlight intensity was above 1000 millimeter. A current test with a clip-on ammeter result in a reading of this maximum level of current. It's very important to note this aspect of your system configuration. Play factor rule. ISC rating of 1.25 radian factor. Now let me see right here. Let me see if anything here is ISC. Come down here, the temperature coefficients. Tell you even the temperature coefficient, the maximum system voltage, the maximum system voltage 1500, safe class 2, maximum reverse current 20 wire ratings. All of those information are available on the data sheet, and the installation manual also has information you will need in relating to that model. Very important, the measurement tolerance STC. So they use the STC rating right here. That's what they use. Minimum, minimum. Now, 1.8. So find the voltage. At least 98% of normal power during first year. Thereafter, max 0.54% degradations per year, at least 93.1% of normal power. So they tell you everything about the power, man. Everything. This is a Q cells panel, very good panel. Tell you everything here. I'm trying to find the output footage. Power at MPPT maximum. Yeah, right here. Short socket ISC. Watts. Operating socket voltage. Current voltage. Efficiency. All right, enough of that. That was just to tell you that you can go to your manual where you can find those information. That's just tell you that the manual, the data sheet of the panel tells you other things, the ISC, and so Now let me see that. ISC times 4. We're saying yeah, maximum socket current. So, so parallel. ISC times the parallel, so socket in parallel at times ISC times 1.25. Our ISC of this panel here, what's the ISC? ISC the short socket is 10.05. So find the maximum. I got it 10.05 times 1.25 equals 12.50. So 12.50 would be your maximum. What did I just do? I came here to the data sheet of the PV model and I seen the ISC ratings, amperes, amps of 10.05. So I take that 10.05 and if I look here by our requirements to find the maximum because we have the minimum. Here they give us the minimum. They didn't give us the maximum. They tell us about the minimum. So in order to find the maximum, this is the minimum. That's why they say the maximum is a standard testing condition, STC power tolerance plus 5 watts divided by minus 0.5. Maximum performance at standard testing condition, STC power tolerance plus 55 watts divided by minus 0.5. That is how you can find the maximum performance at standard testing condition. I want to try that. So standard testing conditions. So we have 5 plus 5 minus okay 10.05 5 and 5 and 0.25 divided by so they say in the power classification, find the maximum performance at standard testing condition, STC, power tolerance plus 5. What is the power tolerance? Power tolerance. Power tolerance. 9.3. Hmm. I want to use this conductor. PV shows an output socket as a sum parallel connection. As a sum socket as the sum at parallel connected PV module rating. Short circuit current times 1.5. Circuit current times 1.5. Number of socket in parallel times ISC 1.2. Right? PV socket output socket as a sum another rating short circuit. 1.5 factors apply to the ratings. Short circuit occurring because certain conditions such as main day. All right. So as we go along, I'm going to do the math. I'm going to do the math here. Find that a maximum socket maximum socket current for this model. You can bear in mind, just keep write this down that the TC the STC ratings for this model here, which is 380 watts of the ISC, which is 10.05. So we want to write that down. We have 10.05. We want to write that down, and we want to later on we do the math to find out what will be the maximum rating. But they're saying right here to find the maximum performance at standard testing condition, STC, power tolerance plus 5 watts divided by negative 0 watts, STC ratings. Don't overthink it. We have to work it later because I have to continue with the trend. All right, we'll work them out. Now let me continue. Get back to that. Power electrical electronics sockets mean maximum current. Inverter and DC to DC converter cannot produce more current than the ratings. DC to DC converter socket maximum current rate continuous output current specified by manufacturer. Inverter output socket maximum current rating continuous output current specified by manufacturer. Inverter rating continuous watts divided by normal AC voltage. Section 690.8 define the maximum socket current or maximum current for DC to DC converter socket as a DC to DC continuous output current ratings as specified by the manufacturer. For DC to DC converter output socket, the maximum current is defined as a sum parallel connection sum parallel connections DC to DC inverter source socket current. Since DC to DC converter will not produce more current than their ratings, the additional 1.25 factor is not required. In DC to DC converter sockets or output socket calculation, model lead consider considering PV source socket size at the factory size at the factory to include a 1.25 factor directly connected to models and may expose additional current from high irradiance condition. For example, in a system with a DC to DC converter source socket, the maximum socket current of each will be rated continuous output current of the converter. 15A for this example, 15 amps for this example. The maximum socket current for the PV output socket consists of those two PV source sockets in parallel would be the sum of both source sockets, 30 amps. Likewise, if there were four DC to DC source sockets connected in parallel, the PV output socket maximum socket current would be 60 amps. Okay. For DC to DC converter system, the maximum current for AC inverter output socket is defined the same way as it is for any other type of inverter output socket, as the inverter continuous output socket ratings. You see this right here, continuous duty. Sockets are considered continuous when maximum current can flow for 3 hours or more. PV system. PV systems and AC sockets are continuous. Continuous operations for more heat produced. Additional 1.25 safety factor adjustment required. PV source and output socket adjustment for continuous duty. PV maximum socket current 1 times 1.25. The ISC times 1.25 times 1.25. Our electric socket adjustment for continuous duty equals socket maximum current times 1.25. NEC section 9.8, 969, 690, when it requires conductor to be sized based on calculated continuous current. Each current in PV systems are considered continuous because they could sustain for 3 hours or more at peak output, meaning meeting the NEC definition of continuous. Socket that will be operating under continuous duty must have an additional 1.25 factor of safety applied to protect them from overload during continuous use. This is separate from the previously discussed irradiance factor and is sometimes referred to as 80% rule, as 1.25 is a reciprocal of 80%. 80% operations equal 1 divided by 0.80 equal 1 times 1.25. When this correction factor is applied, the conductor will carry no more current 80% it rated amplicity. So for PV source socket and output socket, continuous current equal the maximum current times 1.25. This is the same as the ISC times 1.25 times 1.25. The two factors are sometimes combined and state as ISC times 1.256. Continuous current for inverter output socket equals the maximum current socket current times 1.25. Maximum socket current. So there is only a single 1.25 factor applied to inverter output socket because they are not influenced by increased irradiance as discussed previously. By applying these factors to the current in the various sockets, the calculated socket current has increased, and the conductor selected must have sufficient amplicity for this continuous current. The ambient air temperature other than 30 degrees Celsius, 86 Fahrenheit. NEC table 380, 310.5, 310.15b, 2a. Multiple conductors in the same conductor. Adjustment required for 3 plus current carrying conductors in a single conductor. Additional heat raises temperature in conductor. NEC table 310.15. Raceway cable exposed to sunlight on roof must be greater or less than 23 millimeters, 7 to 8 inches above roof, or additional adjustment applied. Hmm, that is interesting. Ambience, air temperature other than 30 degrees Celsius or 85 Fahrenheit, NEC Table 380, 310.15b, 2a, multiply conductors in the same conduit. Adjustment required for 3 plus current. Carrying conductors in a single conduit, additional heat rate rises temperature in conduit. NEC Table 310.15. Raceway cable exposed to sunlight or roof must be greater or less than 23 millimeters, 7 inches above roof, or additional adjustments applied. The condition of use for conductors also must be considered. Heat is a primary concern because conductors' ampacity decreases as temperature and Dux resistance increases. The conditions that increase operating temperature for which conductors, which the NEC provides adjustment for, are high ambient temperatures, exposures to sunlight in conduit or rooftop, multiple conductors in the same conduit. Table 310.15b 2a in the NEC provide factors for producing or correcting conductor ampacity. When the ambient temperature is above 30 degrees Celsius 86 Fahrenheit, this is often the case for conductors in PV arrays since they are installed outside. Sometimes the AC socket may not actually be exposed to higher ambient temperatures. Instead, if the inverter and the associated AC wire are located inside a conditioned space, obviously, areas that experience moderate to high summer temperatures will be affected. Regardless of geographic location, conductors run across the roof, through attics, or installed in other high temperature locations will be subject to increased ambience, thus operating temperature. The multiple current carrying conductor inside the same conduit cause the temperature inside the conduit to be higher because there is more heat on more conductors and less air space for heat to dispense. Dissipate into it. Therefore, NEC 310.15b 3a require a reductions in conductor ampacity whenever there are more than 3 current carrying conductors in the same conduit. This applies to the ampacity of all conductors in that conduit. Now, that raceway or cable exposed to sunlight or roof must be installed greater or less than 23 millimeters, 7 inches above the roof, or an additional 23 or an additional 33 Celsius 60 Fahrenheit must be added to the ambient temperature when calculating ampacity for those sockets. This can result in big increase in wire size and putting conductor that include conductor that close to the roof conductor that close to a roof is a bad idea. That close to the roof is a bad idea. Anyway, because they can catch and trap debris, water, and snow. Hmm, a lot to go over. Let me end this section here. We're going to come to section 3. Second section of this training series with the device terminal compatibilities. And we will go down to the voltage drop and, so forth. Acceptable voltage drop. We'll go through that later, but I want to end this class. Research some material add to our next training section. Now, stay tuned for the second.